Okay, so last time we were talking about parametric equations, which is just another way to represent points in the xy plane. Well, here's a third way to do it using polar coordinates. With polar coordinates, what you do is you have what's called the polar axis. It looks kind of like this. Looks like it's the positive x-axis, and you would you start at the polar axis and you rotate an angle theta. If theta is positive angle, you would rotate in the counterclockwise sense. And if theta is negative, you would start on the polar axis and you rotate in a clockwise sense. And once you rotate an angle theta, then you move a distance along the terminal side of theta. If r is positive, you would extend along the terminal side of theta r units. And if r is negative, you would extend opposite. If you were to draw a line segment along the terminal side of theta, and instead of extending along the terminal side of theta, you'd extend in the opposite direction. And so you could represent points in the xy plane using polar coordinates by an angle and a distance. It turns out there's multiple ways to represent points in the xy plane using polar coordinates. So each point can be represented several ways with polar coordinates, which is kind of a problem actually. Anyway, so let's practice that first. If you wanted to plot this point 2 comma pi over 4, you would start and you would rotate pi over 4 radians counterclockwise, and then you would extend 2 units on the this would be a positive 2, so you would extend along the terminal side of theta 2 units. So this would be the point 2 comma pi over 4. The first coordinate is r, the second coordinate is theta. Here we go. Here you would rotate clockwise pi over 4. In other words, you'd rotate down, and then r is still positive, so you would extend along the terminal side. So this would put you in the fourth quadrant. This point would be right about there. How about this point? Negative 2 pi over 4, so you would rotate counterclockwise, I should say, but instead of extending along the terminal side, you'd extend opposite the direction of the terminal side. You'd be in the third quadrant, right? This point right here, you would rotate clockwise and you would extend in the opposite direction of the terminal side. So that would actually put you in the second quadrant, wouldn't it? Why don't you try this one here? See if you can plot this point. 2 comma 3 pi over 4. Hit the pause button and try this one. Okay, so you rotate counterclockwise 3 pi over 4, and then r is positive, so you extend along the terminal side of theta. Now, what I wanted to point out earlier was this. Notice you end up at exactly the same point. You end up over here. The point negative 2 comma negative pi over 4 coincides with the point 2 3 pi over 4. You end up at the same place. All right. Next thing I want to do is talk about how to convert between polar and rectangular coordinates. All the conversion factors you need to know are right here. It's pretty easy if you think about this picture. You're on the polar axis and you rotate an angle theta, and you end up, this would be the r distance, this would be theta. And notice in the xy, if you superimpose the Cartesian coordinate system, this happens to be x and this happens to be y. So by the Pythagorean theorem, you can say right away that x squared plus y squared has to equal r squared. And if you look at right triangle trig, isn't cosine theta x over r? So x would have to be r cosine theta. Similarly, y would be r sine theta. And the last thing, the way you switch with theta is you would use the relationship that the tangent of theta using right triangle trig is y over x. So here's how it works. Suppose you wanted to convert this point to rectangular coordinates, okay? So first thing you could, if you know r and theta, I would just go right up to here. If you know r and theta, you could find x and y, you see? X equals r cosine theta, y equals r sine theta. So you get this, and then when you simplify, you get radical 2 over 2 comma radical 2. I should say radical 2 comma radical 2, right? Similarly, this one over here, you would do it the exact same way. You would use the fact that x equals r cosine theta, so and y equals r sine theta. So you'd get x equals r cosine theta, y equals r sine theta. You simplify it and you get 2, 0. Okay, let's go the other way now. Let's convert from rectangular to polar. This is a point in the fourth quadrant, right? So if you know x and y, how would you get r and theta? Well, what you could do, if you know x and y, couldn't you get r by using this relationship right here? We're going to use this relationship to find r, and we're going to use this relationship to find theta. Okay? So x squared plus y squared is r squared, so you know that r, you better be careful. I don't know if r is positive or negative. Remember, we allow a negative r with polar coordinates, so don't always assume r is positive anymore. It depends on how you want to represent the point, right? So let's stop with that. Now the way you find theta is tangent of theta is y over x. So when you use inverse trig functions, remember inverse tangent gives you an angle between negative pi over 2 and pi over 2. This is it gives you a negative number. And so this is going to put you at a negative angle, and you're in the fourth quadrant, which is where you want to be. So if the terminal side of theta is in the fourth quadrant, you want r to be positive, right? Because you want it to be along that terminal side. So this is one way to represent the point. Why don't you try this one on your own? See if you can represent this point in polar coordinates. Hit the pause button and try that. Okay, so first I'd find r. I'm going to let r be plus or minus 2 for now until I decide with it. I better end up in the fourth quadrant, right? So as long as I'm in the fourth quadrant, I can use whichever one I want. Tangent of theta would be negative radical 3. I think we know what angle this is. Isn't that negative pi over 6? This is what your inverse tangent is between negative pi over 2 and pi over 2. So if theta is negative pi over 3, you want to have a positive r because you want to end up in the fourth quadrant. So use positive 2 for r. Okay, let's talk about graphing polar equations now. R equals 3. Well, let's talk about this first of all. Why are we doing this? Well, in calculus, there are some areas involving circles and other types of equations that are more easily represented in polar coordinates. And if you want to find the areas inside of these things, the computation, the integration can be a lot easier with polar coordinates. So it's worth using different coordinate systems. It depends on what it is you're trying to do. Anyway, r equals 3, I think you can probably figure that out. The radius is 3, the angle can be anything. Don't you end up with a circle of radius 3, right? If you allow there r to be anything, and theta can be moving around, so you end up with a circle. How about this? Theta can be between 0 and pi over 6, and r can be anything. It turns out there, if you think about it, you get this wedge. Now, you get two of these pieces because if you have any angle between 0 and pi over 6, you don't assume r is positive. R could be a negative value too. That's how you'd pick up these values over here. So you're picking up all possible line segments where r is positive or negative. Alright, now comes the fun part. Let's find the equations in Cartesian coordinates. Let's switch this to xy coordinate system. The way we're going to do that is we're going to use those conversion factors we talked about. The one that works for theta is that tangent of theta is y over x. So what you could do is, isn't the tangent of theta 1 over radical 3 is y over x, so you'd solve this for y, and you end up with y equals x over radical 3. Doesn't that make sense that this should be a, it makes sense that this should be a line segment. If the angle is fixed and r can be anything, you get a line. Actually, you get a whole line. R equals 4, I think we know what that is, but how would you get the actual equation? Well, if you square both sides, you could use this equation. If you square both sides, you get r squared is 4, right? 4 squared. R squared is 616, so you could replace r squared with x squared plus y squared. So that's a nice, slick way to do it. Let's convert back. Suppose I give you the equation in rectangular and I want you to convert to polar. Wherever you see an x squared plus y squared, couldn't you replace it with an r squared? And then recall x is r cosine theta, so you could do that, and so the equation looks kind of like this. Here, remember the conversions are x equals r cosine theta, y equals r sine theta. So you get that, and then you get r squared sine theta cosine theta equals 5. That's good enough. However, you could be sneaky here. You could multiply both sides by 2. Why would you want to do that? Because you know that 2 sine theta cosine theta is just sine 2 theta. Then you could divide both sides by sine 2 theta and get this. r squared equals 10 over sine 2 theta, which could be written as 10 cosecant 2 theta. So that would be a slick way to do it. Okay, by far the most important thing in this section is being able to recognize what certain graphs look like in polar coordinates. So I don't assume you know that, but there's about 4 main ones that you should really learn to recognize. And the way you learn it is you just start plotting some points here and graph it by hand at first. Remember, theta is an angle, so you pick some values of theta. I just picked multiples of pi over 4, and I plugged them in. For example, when theta is 0, r equals 2 times cosine of 0, which is 2 times 1, which is 2. When theta is pi over 4, cosine pi over 4 is radical 2 over 2, but you multiply by 2, you just get radical 2, and so on. Anyway, if you were to plot these points, it turns out you get a circle. Interesting enough, the circle is actually mapped out just between 0 and pi. You don't have to go all the way to 2 pi. Now here's why you only go between 0 and pi. At 0, you're at 2, right? Each tick mark is 1/2, okay? So at 0, you're at 2. And then as you rotate at pi over 4, right about there, then the r value is radical 2, right? So, and then as you get closer to pi over 2 as your angle, the r value gets closer and closer to 0. You see that? So at pi over 2, what you've done is you've mapped out the upper half of the circle. Then as theta moves around into the second quadrant now, r is negative. You see that? In fact, if you're at 3 pi over 4, right about there, if the angle is 3 pi over 4, then r would be is negative radical 2. And if r gets closer and closer to pi, you've gone an angle of pi, r is negative 2. So in other words, you've mapped out the whole bottom circle from pi over 2 to pi over 2. If you were to keep on going here, then what you would just do is map the circle out twice. And that turns out to be really important that you not do that, especially when you're integrating, because you end up getting twice the area that you want. So you have to kind of know how it works. Anyway, but you should recognize curves like this. Whenever you have something like r equals a cosine theta, that turns out to be a circle that's symmetric with respect to the x-axis. If you have a negative number in front of here, I believe what that's going to do, if this were negative 2 cosine theta, I believe that would flip it across the y-axis. And instead of having a cosine, if you have a sine instead of a cosine, I believe it's going to be the same story, but the circle is going to be symmetric with respect to the y-axis. So learn to recognize that type of polar curve, the circles, okay? All right, let's look at another one. Let's look at this one here. This one is 1 plus cosine theta. Okay, so if you were to plot some points, you end up getting a curve that looks like this. It's called a cardioid. It's kind of an interesting graph. And this one actually takes 2 pi to map the whole thing out. What I want to do here is I want to show you how to actually graph these on your graphing calculator. That's what we'll do in the next video. Let me wrap this up, and we'll look at the graphs some more. But the summary is this is called a cardioid. This type of graph is called a cardioid. Whenever you have a plus or minus b cosine theta, as long as a is greater than or equal to b, you get this heart-shaped graph. Okay, so a would be 1 and b would be 1. Now, if this were a minus instead of a plus, I believe it flips across the y-axis. And if you had a sine instead of a cosine, it would be symmetric with respect to the y-axis. Anyway, so in the next video, part 2, I'll show you how to graph these on your TI calculator, and we'll do a couple more graphs. All right, we'll see you then. Bye-bye.